All right, well, we'll see. Mine's not working. Okay, so Hamiltonian operator. It's minus h bar squared over 2. What's the h bar? That should have been in our concept preview. H was Planck's constant, right? 6.626 and 10 to the negative 34 joules seconds. H bar just means divided by 2 pi. H bar is Planck's constant over 2 pi. So don't let that worry you. So this Hamiltonian operator, h bar squared, well, it's negative, over 2m, and m is just the mass of whatever the little particle or object is, second derivative plus v of x. We're almost always going to say that's the potential energy at position x. And we're almost always going to say it's 0, because our mathematical operations that we're going to do, you see what's coming up, integrals, it's ugly enough without including this complex, how does x's potential energy change with position? We're almost always going to say that little ball is just rolling around at the bottom. Doesn't matter where it is, as long as it's in the box, the potential energy is 0. Just rolling around on a flat surface. Okay. But we don't have to. So that's one dimension, because all you see is x. And then you have 3 dimensions, x, y, z. That's why they have the del squared in there. Okay. So the reason why they're so big on this Hamiltonian operator is right here. Because when the Hamiltonian operator is operated on our wave function, you get the wave function back again, but then you get a number. And that number corresponds to big E, which is probably energy. So that's the Hamiltonian operator. If you apply it to the wave function, you get the energy and the wave function back again. Now, it's not just any wave function. It has to be the wave function that corresponds to the system that you're using. It has to be the correct wave function that gives contains all the information that you need. Right? It's this abstract idea, this abstract mathematical function. But if it's correct, you apply the Hamiltonian operator and you get the energy every time. Okay, and the wave function back again. So since when things are working and they're working correctly, that's the only thing we're supposed to really be talking about, when things are working correctly, well then these operators operate and you get a eigenvalue. So they fit this format. So they're trying to say that there's our operator, and omega is just the general form of writing an operator. I don't know why they picked omega. Big G for general or something, but they picked omega, fine. So omega is any operator you want. Operates on any function f. Then you get a number times a function back again. And that number is called the what value? Eigenvalue. So there's your terminology. You've got eigenvalues is omega. Then f would be an eigenfunction. Eigenfunction. So eigenfunctions, little f, eigenvalues, little omega. Assuming that it works, right? It's not always going to work. What if you don't get the function back again? If you don't get the function back again, it doesn't fit this format. You can't say eigenvalue and eigenfunction if it doesn't fit this format. You have to get the function back again. So that means our function, if you're going to, especially, look at all these derivatives. Our function is really going to, we don't have very many choices. If you're going to take derivative and you want to get the function back again, what functions will we probably be talking about for wave functions? Sine. Sine and cosine are great, because you take the derivative of sine, you get cosine. But it's not just the first derivative, it's the second derivative. So then you get the sine back again. Now there's another one. E, that exponential. You always get the exponential back again. So we're pretty much stuck to those functions and those functions only for our wave functions formats. Otherwise it's not gonna fit. A linear combination, all that is let's say g of x is your big function. Well, let's call it little a times f of x plus little b times, what's after f? G? No, I can't do G. You already made up G. That's H of x. And then little c times I of x plus little d. See what I'm doing? I'm just adding up in a linear fashion, I, j. Adding up in a linear fashion to make another linear equation. So they call that a linear combination. And this A, B, C, and D are just coefficients. But I think this looks more like a blank sum. Starts with a W. E, I, weighted, a weighted sum, right? Because if the bigger that coefficient, the more important that one little function is, right? A weighted sum. So now they're getting into this idea of superposition. They're just saying that this wave function is a weighted sum of all these other little tiny wave functions. And the reason why they're doing this is because there's one equation, there's one system, there's one thing in nature that can be solved exactly by the Schrödinger equation. You know all the energies, you know the wave functions, everything, it's perfect. It's solved. What's the element? Can't get any simpler than this. Hydrogen, because it has how many electrons? One. More than one electron, and things are already getting so ugly and so complicated, they can't solve them exactly. So what they're going to do is, we know the solutions to the, so as a starting point, we know the solutions to all the orbitals, right? All their wave functions for the 1s, the 2s, 3s. I don't know if we've ever actually seen them written out, but we will. It'll come up. And so this could be the 1s, right, times its coefficient, plus the 2s times its coefficient, plus, and just list them all out. And you can mess with these coefficients to optimize this wave function so you get the best energies. And that's what Spartan's doing a lot over there. Okay. Now what's kind of weird is, okay, what are the odds of me rolling a 6?
1 out of 6.
1 out of 6, right? 1 out of 6. That's the odds of me rolling a 6. But if this was the size of an electron, probability doesn't go that way. We know that there's 6 possibilities. Okay, so here's how probability goes. I have to square that little weight factor and take its absolute value. So we know that there's, before we would have said, well, let's back up a little bit. Let's say, what's the odds of rolling a 1 or a 2? What are the odds?
2 out of 6.
Yeah, it could be 1/6 plus 1/6. Yeah, right? Roll a 1 or a 2. The probability of that would be 1/6 plus 1/6, right? 2/6 or 1/3. 1 chance out of 3, right? Everybody agree? Now it's supposed to be a die that's the size of an electron, extremely small. Quantization now becomes important, and the coefficient is 1/6 still, because you have 6, all these numbers 1 through 6 that are all equally possible. So each coefficient is going to be 1/6, but you have to square those coefficients to get the probability. So 1/6 squared plus 1/6 squared, I think is like 0.1 or something like that. It really doesn't matter. The point is that it's not 1/3. And this is how statistics or probability is added on the microscopic level. It gives the right answers. Why? It's because, everything, it's a strange world. Okay. So now we're getting to the point where if you make this out, apply this Hamiltonian, you're applying it really to that one wave function, and that one wave function where? I mean, it's either an x, one dimension x, or xyz, 3 dimensions, or spherical polar coordinates, whatever you like. It's, this is going to be changing depending on where it's at. So if you want to get the true observable, the true energy, you need to integrate over all the orientations and all the possibilities, all the likelihoods. That means integral, right? Not just one. Like, you need to integrate over everything. So this is really what's done in, if you want to say in the lab or in the real world. You want to know what the position is. You want to know what the energy is. Well, you're talking about a real-life observable, and that has to take into account all possibilities. So you have to integrate over all possibilities then. And that means integrate. So how does it look? This is just their way of doing it. And they call it expectation values. So again, omega is our general operator. It could be, and it makes the most sense if you pick an operator, not like the Kevin operator that raises it to the 4th. That doesn't have any observable meaning. What does that mean? Raise something to the 4th power. There's no observable there. But energy, position, momentum, the 3 made guys, yeah. So you can look at energy. So you put in whatever operator corresponds to energy, right? And that's going to be h. So this would be h hat equals the integral, the wave function, h hat, the wave function again, d tau. Okay, and then this operator is only operating on the wave function right here. And we'll be playing around with that. But that's their idea. That's the language that we just, I guess, need to get used to. Okay. There's another odd thing going on here. Let's say, you remember the de Broglie story. P was h over lambda, right? And P was what? Momentum. Linear momentum, right? So mass times speed, right? If you know what the linear momentum is, just say you know it, well, then you know what the wavelength is. Okay, well, if you know P, if you know P, then you know the wavelength. Right? Just simple math. So plot out the wavelength. I'm not very good at drawing, but you try to draw a sine or a cosine wave. This keeps on going, right? You know the wavelength, so I don't want to change my wavelength, but where is it? You have no idea. So it's kind of like what they're trying to say here. They're trying to say that there's our little h bar popped up again, right? These deltas are uncertainties, or if you're going to make this measurement, what's the possible range that you're finding? Okay, and so if you do a really good job on one, the other one gets a lot worse because they're inverse. If you solve for, let's say, like we said that we know momentum. If we know P, at least all measurements have air with it, plus or minus something. But if you know something really, really well, that range should be really small or really big. Really small, right? That uncertainty, or that error, whatever you like to call it, I think uncertainty is what we should be calling it. That's what they're saying. So if that's really small, well, if we mess around with this, right? If that uncertainty is really, really small, it's in the denominator now. That means delta Q is just going to blow up. And the reason why they give it a Q instead of an X, Y, or Z is because it could be X, Y, or Z. Right? If you're talking about, remember, is momentum a vector?
No.
Yeah, because it's mv. Is m a vector? No, it's scalar. But v is a vector. So that means it could have an x component, a y component, and a z component. So they should be writing this 3 times. They should be saying delta p with little subscript x. Delta x greater than or equal to h bar over 2. delta P with a little y, delta y, h bar greater than or equal to h bar over 2, and the last one with the z's. So that's why they have a q in there. Just substitute in x, y, or z. So the uncertainty, if you really know, if you nail down delta P in the x direction, right, then the uncertainty, just like this, you can have no idea where it's at. The range is huge. Okay. So these are 4 parameters. So this always works. That story where you have these two guys multiplied together and this uncertainty principle relationship, it holds for these parameters or these observables or these measurables, whatever word you want to put on there, that do not commute. Do not commute. So we're on this word. Commute just means order doesn't matter. Order does not matter. Right? For example, 2 times 3 is equal to 3 times 2, right? Order doesn't matter. That's kind of a weird way to say those guys are observable or operators, but it could be, right? You're going to multiply by 2. That's your rule. You're going to multiply by 3. So, but the order doesn't matter. So they commute. These guys don't commute, right? Because p hat that's how you define the operator of momentum in the x direction, d dx. X hat is just multiplied by x. So if you took the two and try the order, p hat, x hat, is that equal to x hat, p hat? Right? So what they're saying is p hat is h bar over I d dx times x. Well, you take the derivative of x, you just get 1, right? So you just have h bar over I on this side. Does everybody agree? Over here, you end up with x is on the other side now. You end up with x times h bar over I d dx. And you can't simplify that anymore. It's done. They're not the same. So they don't commute. So they don't commute, so you can write this funky little relationship with Heisenberg uncertainty principle. So that's kind of what they're trying to say. So there's a lot of saying the same thing over and over again. This is, again, they don't commute. They meaning these observables. Another word for observables is operators, right? Operators that don't commute. Then you can write something like the Heisenberg uncertainty principle with them. So it's just a lot of terminology that we just need to get used to and play around with. One thing that's kind of cool here, I wanted to show you. So these are harmonics. And if you take any harmonic, look, we can't hear it. There it is. All right? You have all these different harmonics. See how they're plotted out? Lower frequency, all right? Longer wavelength. Right? Make sense? Okay. So these are a sound, you know, frequencies like this. But all I'm trying to say is these are cosine waves or sine waves. Right? It's kind of like a wavelength here. It is a wavelength. What would happen if I just crank up all these guys? What would happen? Now, what I want you to picture here, though, is this is analogous. It's getting nauseating, isn't it? That is analogous to what we're doing here. See, if I add this wavelength, here's a wavelength. It goes on forever and ever and ever, just like in that, what we're going to hear, the sound. Add it to another wavelength, add it to another wavelength, add it to another wavelength. We're not going to have, in the system, in this linear combination here that we're talking about, where'd it go? Our equation for linear, here it is. Each one of those guys, each one of these is a possible energy state or a possible energy. That means it's a possible wavelength, maybe. Well, if you add up all these possible wavelengths, you're going to have no idea. You know, it's the energy, you're taking into them all of them into account, but you'll have an idea what the position is. And you can visualize that with this. So I'm going to add this wavelength to this system. I'm going to add this wavelength to this system. So I'm going to keep adding all these wavelengths up. We're going to have less and less idea in this tone what the wavelength is, but we're going to know where the position is. It's going to get a center. I guess the word is a center burst or something. See I should zoom out here. How do I zoom out? Auto scale? Oh, auto scale. See, look what's happening. Right? And if I had even more, man, we would get a real nice center burst here. Right? And the less I have, so I have an idea, I have no idea what the energy is, but I have an idea of the location. If I want to know what the energy is, that means I got to have just one of these dudes, or less and less. Notice how I'm losing information on the position. It starts really spreading out. I begin to find I have no idea where it's at anymore. All right? Okay. So that's Heisenberg uncertainty principle. Handout, chapter 11, day 4. Oh, there it is. Okay. So, I don't know if we want to jump down there or maybe just start here, right? Oh, you don't have those. Do you have those in there?
No.
Oh. Well, we can blow them up. And then you can say the answers. Because I think these are just conceptual. That's why I think it'd be good for us to talk about them. Blow them up here. Okay, so this is the homework. Self-test 11. You don't need to write the whole thing down. Just write self-test 11.5. All right? Self-test 11.5. And this is the question on it. I'm not sure what page it is in the book, but these self-tests are in the reading. So self-test 11.5. So Mel, is the function cosine AX an eigenfunction of ddx? So, and with this PChem stuff, I don't know if this works for you. You'll find out. But what works for me is to have these keywords in the question, and then that brings out some math relationship. When I see eigenfunction, this is what I'm looking for, and everything that has to do with it. So, is cosine AX an eigenfunction of ddx? Does it fit that format? Well, you get an eigenvalue when you get the function back. So do you get the function back? Right. What would it look like? It would look like this. Plug in, for omega hat, plug in the dd, plug in whatever the operator is. It's ddx. For the function, plug in what it is. It's cosine AX. Well, what would you get?
Negative sine AX.
Negative.
Negative sine.
Oh, yeah, don't forget about that A. Thanks. Negative A sine AX. Okay. It's kind of cool. Looks like we have an eigenvalue, but do we? We don't, because we don't get the function back. So the answer is no. How about B? Huh, why do I have the answers here? Okay, if B is yes, Jeffrey, what is the and B is yes, what is the eigenvalue?
Negative a squared cosine ax.
Okay, let's try it. So now we're supposed to have well, we take the first derivative, and we've got this guy, but we're supposed to have, it's supposed to say d2 dx squared, right? So we have, move this over a little bit. I still have a derivative left. So he's taking this derivative. He's trying to figure it out. So I take the derivative of this again. I get what? What's out front here? Negative a squared. Well, we can write it this way if you don't see it. Because I have my negative a, and then I take the derivative sign, and I'll get cosine ax, but then I have that a again. Then I have this cosine ax, right? Okay. So omega hat f is really equal to this. So my omega part is going to be what?
A squared.
Close.
Negative.
Negative a squared. Okay, that'd be the omega. Okay. Self-test 11.6. We need our book to follow that. What you'd want to do is find the self-test 11.6 in the book, and because they did a nice example before that. That's why they're self-tests. They have this worked out one, and then they have a little thing to make sure you understood. So I would find the book 11.6, and it'll be nice and well organized, and follow their format. What time did we start?
1:45.
1:45. Oh man, we have all this time yet. Okay, let's jump to our handout. Get you started on that. So you wrote your functions, right? What are they? Would you write in A? Write the three complete.
Right?
Mm-hmm.
Psi was 1 over the square root of A.
Oh.
Yeah.
Oh, whoop. Okay, and then how about for B?
Square root of 3 over L raised to the third times x.
Shouldn't be an X. Oh yeah, sorry. Right after the whole thing. And the whole thing is squared, not just the 3. I mean, that's
Oh yeah,
square root.
my fault.
Oh, it's the square root of this whole thing. Okay. So there, make sure everybody agrees with these. All right. How about C?
We didn't do that one because you said you messed up.
Oh, okay, messed up. And how about D?
Square root of 1 over over 2 e squared minus 1 times e.
Oh my goodness. What?
Erase
Okay,
that.
yeah, erase that. So big square root 1 over L over 2 times e squared minus 1.
It's on the bottom.
Yeah.
You sure you did that right?
Yeah. We have to say that. We did that.
Hmm?
All in all
I'll
that
take the square
time.
root e to the x over
I
L.
want to make sure that we're getting all the same stuff here. Where the heck is my stuff? Huh.
for?
Because like, we have at least 10 numbers and give it to the XLB output.
I mean, you have,
So I didn't know about that. I would have had that out instead of this sheet.
I thought I had all this stuff in
you
here.
should just write it down.
Let me do ID first.
So,
Because I
what if
did
you
that
just
one
text
last
him?
time.
Text him.
I'll do it. You take the ones that I know, and then that should be fine. I'm not sure.
I don't know where it is. All right, well, if you guys all got the same answer, it should work out. It just looks weird.
Maybe you can simplify, but we didn't do that. And then there's one more thing you gotta add.
What do I have to add to it?
Times e to the x over l.
Oh, okay, that's looking better. Okay. Determine which above normalized wave functions, if any, are eigenfunctions of the momentum operator. Okay, so the momentum operator, there's several that we need to worry about. There's h hat, and they gave that, see the notes for that. There's p hat, which is h bar over I d dx. And there's x hat, which is just x. Okay. So for the momentum operator, can you see any of these being eigenfunctions?
First one?
Well, there's not even an x in it. You take the derivative and you're going to get 0. I guess you could argue that, because then you could say that the eigenvalue is 0. I guess that might work. I guess that you can kind of, but that's not, it's kind of weird.
So
But
then the second one?
take the second one. You need to get the function back again. Take the derivative of x, it's gone. Right? Because you have to take h bar over I d dx of that.
Oh, that's what you said in the beginning of class where sine and cosine
Yeah.
will always come back and an exponential function
Yeah.
always come back.
Sine and cosine will come back if you're taking the second derivative. Here we're only taking the first. So sine and cosine functions aren't going to work either.
maybe the last one?
Your only choice is the last one. That one will work. So see if you can figure out what its eigenvalue will be. See if I can find that self-test. 6. You guys didn't bring your book, right?
I brought my book.
Well, we may not have time to get to it anyway, but we'll see. Self-test 1.6. So you should end up with, you'll have an h bar over I there for sure. You'll have that whole thing there. And then you take the derivative of that, you should get a 1 over L. Shouldn't you end up with that as your eigenvalue? Right? Because you're going to have, oh, but you want to get the function back, and the function includes that. So you wouldn't include that. Yeah, I can't skip stuff. for it to fit this, wouldn't you just end up with this for your eigenvalue? Because it's going to be the whatever you can pull out, that's the only thing you can pull out, because the rest has to be that function back again. And this thing that I circled in red, that's part of the function. So you have to get this whole thing back again. So that, when you do this, you're going to get h bar over I, 1 over L, and then times this whole big thing. Didn't you? Didn't you get that? Because that whole square root of L over 2 E squared, that's just a constant. You pull that right out of the derivative. Are you guys seeing what I'm doing or not? Alyssa, did I lose you?
No. Yeah, well now I understand, because you said everything under the square root is a constant.
Yeah.
So you're only
There's
doing
no
the
x in there.
x over the L. Oh, okay.
Yeah, the only thing you got to take the derivative of is the e to the x over L. If you take the derivative e to the x over L, you get e to the x over L again. But then you got to take the derivative of the exponent, which is 1 over L. So I get an extra 1 over L. And have that extra h bar over I in the first place. So I get my whole function back here again. So this has to be my eigenvalue.
All of that is a constant?
Anything that's not x, is a constant, right? X is the only thing I'm taking the derivative of, so x is my only variable. Okay. So Glorianne, you see that? Okay, so if take a look at, this is self-test 11.6, so you might want to stand or come over where you can see it. Oh, Mel, you can't read upside down. No, you can't. You can't read. You can't hear. You got to see. You have to see. Come over here. Go right over there. Gloriana, come over here. Jeez, you're so lazy. Okay. So self-tests are in the reading. So here's self-test 11.6. They wanted to find the expectation value of R. And all they're saying is this goes right in the middle. So when we find the expectation value of R, they put their R in the middle. Okay, now where's their wave function? 11.4. So that gave the rest of their wave function. That's where all that other stuff was coming from. Where's that at? 11.5, 11.4. Okay, here's 11.4. Here's their wave function. That's where all this stuff is coming from. So this whole thing is psi. So if you want to do an observable of R, all you have to do is just put R in the middle. Now it has to be psi star psi. So you have to write the integral. You have to write this whole thing. You write down what's in the observable, that R, and then this whole thing again, d tau. So that's what they did. Okay. So where's this? So that's how they got the e to the negative 2r over a naught, because they had the e times the e. I thought it was r. Where's r cubed coming from?
R squared.
Because of the d tau. Right. Remember, because that d tau is r squared dr sine theta d theta d phi. So you have no choice. You have to go 0 to infinity wherever you have r. You have to go from 0 to pi wherever you have theta, and 0 to 2 pi wherever you have phi. So these two things you're going to be doing a lot. You end up with 2 times 2 pi, right? When you do that integral, 2 pi when you do this one. So that's going to happen a lot. But when you evaluate this one, that constant just stayed there. Here we use that n factorial rule, r to some power. I think it was that. So that's your n. So it's 3 factorial. Remember doing that? So that's how they evaluated that integral, because it fits the format perfectly. And they got their answer. Okay, so that is the expectation value of the average radius. The average radius of, what was this, a wave function for? Hydrogen atom or something. Hydrogen atom. So the average position of this electron is 3/2 a naught, and a naught is some constant, so 79.4 picometers. So that's the average distance an electron is in the hydrogen atom. Then if it matches experiment, dang, our wave functions are perfect. If it doesn't match experiment, then you got to mess with that wave function. Okay, now self-test 11.6. Notice how they wanted to find r, so you put r in the middle. Now they want you to find r squared, and then these brackets mean expectation values. The brackets mean do this whole thing, right? Right. The brackets mean do this, right? The wave function, what's in here, wave function again, d tau. So what's in here now is r squared. So we have to put r squared in there. It's really the only thing that changes, except when you're all done, you get your answer, take the square root of it. So that's the root mean squared distance. So that's what you have to do in this self-test 11.6. You have to follow this exact same format. Expectation will be r squared, square root. You have to write a big bracket around this whole big thing and write square root, okay, so you don't forget. And then it would be the psi star, r squared psi d tau. And that psi is way over here. So the only thing that's going to change is this is going to be r to the, yeah, one more r. It should be one more r, yeah, r to the fourth. The only thing that's going to change. So then this thing changes. Just don't forget to take the square root of your final answer. It's not so bad. Right?
Not so bad. Once you
It's
explain
just
it like that.
the reason why is just you just got to take it on faith that it works, that gives the right answers. Has yet to be proven wrong, all this quantum mechanics stuff. So that's good. It's just weird that it only works for electrons. Why not baseballs? Okay. So we have 5 more minutes. How come we have so much time today?
It's 2:35.
Yeah, we
We
were.
went over 5 minutes.
Oh, we did?
Yes.
What was your question?
Number 3, energy operator.
Oh, okay, energy operator. If you're going to do, so we did the momentum. Where do you see energy operator?
On the 4th question.
Oh, number 4, not number 3, number 4.
That's number 3 on my book.
Huh, okay.
Oh, yeah.
So then, would any of them work? Now you got to take, energy is the Hamiltonian. That is the second derivative in it. Would any of them work? The E again. Yeah, it doesn't matter how many times you take the derivative exponential. You always get the exponential back. So you'll have an answer.
Which one is that? Oh, this one over here.
Yeah. It'll be the last one again.